Hello everybody. Just a few words to introduce myself. I'm Stefano Di Paola and CTO at Mandate Security, which is an application security company based in Italy. I'm one of the founders. I just manage of the research at Mandate Security, and I'm the director of research and development at OWASP, the Italian chapter. And my security research is about flash security. I'm the author of Swift Intruder. I do web stuff and web security stuff. My weblog is ysec.it.
I'm Kuza55. More or less, I'm just some random hacker. I like breaking things. I also work at an information security consultancy called SIFT. We do a bunch of app testing mostly, though we do some risk stuff as well. That's pretty much me. So today what we wanted to talk about were some DOM-based XSS stuff, which sort of has been looked at a bit in web app circles in like one or two papers, and really look into how browsers implement JavaScript and how they implement access controls and similar things, and what kind of trickery we can perform there. Also, we're going to talk a little bit about Google Gears. We did this presentation before last month at RuxCon down in Australia. Since then, Google have fixed some things, but we still think letting you know about what was there might be interesting. And we'll also show how typical like XSS bugs in specific places in browsers can actually get you code execution. So, DOM-based XSS was sort of discovered in like 2005, resumed in 2005. It's essentially where you have JavaScript on a page which does some kind of unsafe operations. For example, if it got some data out of the URL and decided it's going to execute that as JavaScript, there's no typical XSS bug where things are being injected onto the page, but you're still able to execute JavaScript because you can control where the URL is. So the paper that Amit wrote talked about some kind of the basic inputs and basic sinks for DOM-based XSS. It talked about like what objects in JavaScript an attacker can control and what sinks in JavaScript it would be useful for an attacker to control input to. It didn't really talk about control flow at all. It pretty much assumed that control flow worked exactly as the language specified, and that the same origin policy was enforced properly for everything. We'll talk about that a little bit later. There was one blog post this year by Ori Segal from Watchfire where he talked about how if JavaScript objects are referenced in such a way that they're, say, referencing objects of parent frames that they think will exist, we can construct HTML files in such a way that the objects they're accessing don't cause a security exception. Yeah, go to that URL to read about that. That's not really what we wanted to talk about. Just to give some background, in the original paper, the Amit client talked about how the attacker can control things such as the URL in JavaScript, which is the first three, the referrer, and the location. It was pretty much assumed that that's where you're going to get all your input from, and then if it goes to one of these sinks where it either writes attacker-controlled input into raw HTML or modifies the DOM in such a way that causes JavaScript execution, for example, via JavaScript URIs in forms or by simply executing JavaScript, or, of course, replacing the URL, or a bunch of other, essentially, actions that could possibly result in script execution. So if you have input coming from one of the sinks, which was essentially the URL or the referrer, and it was put unsanitized, from those inputs going to those sinks unsanitized, then you had a DOM-based XSS vulnerability. The problem here that I see is that all of those sinks focused on direct script execution. it's kind of like auditing, say, some PHP code and looking only for eval bugs where you can execute PHP code. There's a bunch of other things that you'd want to do. For example, on the server side, you'd want to be able to read files or inject in SQL and similar things. On the client side, there's also similar objects you want to access because there's no point in executing JavaScript unless that actually gets you something. So we want to be able to look at JavaScript code and look at if the attacker can force that code to modify or abuse some kind of sensitive objects, such as HTML elements or DOM elements, or leak or edit cookies, or perform some kind of client-side directory traversal attacks, and these kind of things. So, in the original paper, the HTML link that was pretty much the only one presented was the form action attribute, or like a link action attribute. If you can inject a JavaScript URI into one of those, and the user either submits the form or clicks the link, then the user's navigated to the JavaScript URI and the JavaScript executes. However, there's a bunch of other HTML tags that lead to essentially just completely unfiltered script execution. This has been studied fairly in depth by people looking into standard XSS bugs and all the different kinds of tags that lead to script execution. For example, JavaScript URIs and image tags, or being able to control the locations that Flash files are loaded from, and all these other kind of things. We need to start auditing like JavaScript for the ability to edit these kind of special objects and special attributes, rather than just looking for straight injection type things that earlier papers looked at. Yeah, so of course there's injections to CSS and other things. But essentially anywhere that you'd typically, any kind of tag that you'd use for a typical XSS attack is a tag that you need to look at as a sink for a DOM-based XSS. So, yeah. And then on top of that, you have the more non-standard type of XSS things that will work in your reflected XSS issue, but which you, again, people aren't really auditing for in DOM-based XSS bugs. For example, if you have a link such as the one there, which isn't all too common but sometimes happens, those kind of links actually also don't just execute the JavaScript, but they also write the result of that to the page. So, for example, in this case, if someone clicked on that link, then the string user underscore input would be written to the page as HTML. But this is really all more or less old stuff. We need to also think about like the kind of sensitive objects that are in there. CSS is an interesting example because at the moment we can jump from CSS into JavaScript in a lot of cases, but browser manufacturers are doing their best to shut this down. However, Stefano and Sir Darkat have discovered that in the latest CSS spec or the HTML spec, being able to inject plain CSS, which doesn't execute any kind of JavaScript, is still dangerous because the CSS in the latest drafts can actually read values from the page and leak them offsite. We'll talk about this a bit later as well and do some demos, I think. Yeah. Okay. Other things that are usually considered like hard to do, such as spoofing the referrer. It's usually possible to strip the referrer header from HTTP requests, but being able to spoof it and control where it comes from is usually considered difficult and a bug and eventually gets patched. But if you have the ability to control the location of an image tag, either through straight XSS or more commonly through DOM-based XSS, where JavaScript simply edits the location of an image tag, then you can spoof the referrer of a request, or you can leak the current location in the referrer to your site, or even control the user interface, which, while usually derided as irrelevant, does help you with other attacks. Of course, yeah, typical JavaScript injections into links also work, as we mentioned before. But being able to inject links by themselves, even if they don't actually lead to JavaScript execution, still gets you something, gets you a link on the page, which does actually have the referrer of the same domain. This is useful, for example, to bypass IE8's XSS filter, because that uses a same domain check to check whether it should be filtering requests or not. So if you inject a link onto a page and then through some method entice the user to click on that by some kind of either UI redressing attack or just some social engineering, then the IE XSS filter will be pretty much bypassed. And of course, injections into input tags are useful when you're trying to do some kind of like clickjacking style attack where you're enticing the user to click on a button to bypass CSRF protections. You need to be able to fill in input forms, and sometimes you can do this from the JavaScript that's embedded on the page. Yeah. And when you look at some of the JavaScript code out on the internet, a lot of it ends up being packed in such a way that it takes up much less space. Often this means that things are referenced using array notation. So, for example, you'll have like document, then open square bracket, some variable, close square bracket. If you control the contents of that variable, then you can obviously control where something is being assigned or where data is being accessed from. So for example, if you were able to control the index of a read from the document object, you'd be able to set that index to cookie and then potentially leak those offside if there's if the some var was used improperly. And of course, it goes the other way around. If you set, say, user input to location, you somewhat control some var, then you'll also be able to set like the location of it, and which would lead to script execution. This is particularly useful not just for DOM-based XSS bugs, but for typical straight injections, like in reflective XSS attacks, where you need to bypass some kind of IDS. An IDS can only know about the objects that exist by default in the browser. If you modify some kind of variable that's sensitive to a JavaScript application, such as like the index it uses, you can easily modify the control flow of the JavaScript, and then it's pretty easy to lead for that to lead to some kind of script execution, and IDSs really can't pick up on this. So, yeah. A quick detail about the IE8 XSS filter. As I said before, it only filters things cross-domain, but it took the bold move of trying to stop injections into straight JavaScript. It works to stop direct script execution in JavaScript, but using our knowledge of like the sensitive kind of objects that are in JavaScript, we can easily, for example, leak what's in the cookie object or change some variables and these kind of things to change the control flow, which will lead us to DOM-based XSS bugs, which we can later exploit. Yeah. So, some new things we wanted to talk about. The document.cookie usually isn't really considered a sync because reading and writing cookies isn't considered sensitive for some reason. Sorry, writing cookies isn't considered sensitive. However, there were some good papers a while ago about how being able to set a user's session will lead to session fixation attacks where you don't need to leak a user's session identifier, but can simply control it and then have them authenticate to it. With document.cookie, it actually passes any kind of input that you set to it. So if you set document.cookie to equal A equals B, then a new line, then C equals D, two separate cookies, A and C, will be set with the values B and D respectively. On top of that, when we're trying to, when we're writing XSS payloads, we often use the XML HTTP request object to make requests to the site to get like CSRF tokens or perform actions and these kind of things. While this kind of interaction is usually not possible via DOM-based XSS attacks, it is possible to find injections into things like URLs. So if the app uses these like nice pretty URLs where things are separated by slashes so that search engines can find them, if you can control one of the parameters, you can perform client-side directory traversal attacks. And often if the site is using some kind of referrer checking or is using global tokens where a token for one action will be valid for another, then this will let you either perform actions, perform actions on the site that are normally considered CSRF protected. Yeah. Of course, there are other sensitive objects inside the JavaScript, such as document.domain, which controls whether how strictly the same origin policy is applied. browsers are building things such as client-side SQL databases into the browser. I think this is only supported so far by Safari, Chrome, and Google Gears, but it's in like the HTML standard. Browsers expect that they will implement this. And so what we're trying to get at here is pretty much that there are more and more syncs being added to the browsers because there's a lot of syncs and sensitive objects being added to browsers so that developers can create more. But as more of these get added, we have, well, essentially just a greater amount of syncs that we can hit to do things that aren't necessarily JavaScript execution. Of course, so far we've only been considering pages where we control nothing there at all, where all we have is the ability to set the URL, the referrer, and these kind of things. However, there are a lot of sites on the internet where being able to create links or post images and these kind of things desired functionality, such as like Facebook, MySpace, IM, Twitter, whatever, where that ability actually gives you some limited control over the document object model as seen from JavaScript. For example, when some JavaScript tries to get some input from the actual page, it might use functions such as document.getElementById, which is meant to look at all the IDs in a page and then return a reference to a specific object. But a lot of these don't actually do what they're called. For example, document.getElementById gets elements by name as well. And there's a lot of undefined behavior. Mostly, since this is meant to return only a single object, if there are objects with if there's more than one object with the same ID, browsers have to make some kind of decision on what they're going to return. Some browsers return a whole array of objects. Some of them return just the first element with that particular ID or name. But essentially, what we're trying to show here is that if we have some kind of limited control over the HTML on a page, even if we can't use that to get some kind of script execution, we can often use that to bias the control flow of the JavaScript on that page. Of course, there are lots of other inputs other than the location ones, referrers, and things we've described. There's the cookie object, which, while we consider it a sync, it's also we also consider it an input, because though there are attacks that can be carried out when you can only set cookies, it doesn't let you do absolutely everything. And so inputs from document.cookie are often considered trusted by developers, and we often see JavaScript which pulls out a URL from document.cookie and just redirects people to that URL. Sorry. And yeah, browsers are implementing a lot of these different kinds of objects which give an attacker lots of different ways to actually inject input into a JavaScript context that you're trying to attack. Yeah. What we haven't talked about yet is the fact that the control flow doesn't actually work because it says on the tin. An if-else statement can look like one thing's going to happen, but much like integer overflow issues, due to implementation things, control flow might not work exactly as you think it should. We'll explain a bit more about these in a minute, but one of the things we haven't looked into yet, but looks like good ground for future research, is concurrency bugs. Since JavaScript is actually multi-threaded, there exists usually a thread per page, and it has absolutely no support for locking or anything. This usually isn't a problem, as most JavaScript apps don't actually share state between frames, but browsers are bringing more and more ways to share objects and things, and developers are constantly trying to push boundaries and trying to get things like this. So it's not unlikely that we'll actually find apps that try to force some kind of shared state, even though browsers don't intrinsically support it.
Okay. So we have talked about, Alex has talked about DOM-based cross-site scripting. At the beginning of this year, I tried to understand what can be done browser by browser in a DOM context and in a cross-frame context. And this research led to some kind of browser-based DOM XSS. What is it? It's browser dependent. It's based on window references in JavaScript and in the trust relationship between these references. And it's based on cross-frame or also on references of the windows. And just see what the research was beginning by trying to see what a window reference can write or read from another window. Okay, of course the windows are from different hosts. The research, the script was quite simple. It's just trying to get a reference in such one of those ways, and trying to use methods like this in order to understand if there's an exception triggered or if it's allowed. The same for the write. So we try to write an object of another window, and if there's no an exception, then you probably are going to write it. Okay. The same for the brow compliant browsers of getter and setters methods, and these were the methods. So the test bed was something like this, okay? The outer frame is from an host, let's suppose an attacker host, and the inner frame is from a victim host or anyway another host. So by trying to overwrite, you can see that these are the objects you can get or you can read from the inner to the belonging to the outer frame, and these are this is Firefox. These two are the objects that are supposed to be overwritten. Now the results on Firefox. First of all, I have to say that Firefox 3 uses just uses post message, so you cannot read anything or write anything from another window. The results are from Firefox 2, and for example, if you can just overwrite every object inside the history object, also method. So there could be some kind of communication between the two frames. Of course, if there's something sensitive in the argument, it's okay for an attack. Or maybe it could be used in order to bypass, for example, some control or some browser control like anti-XSS or something like that. If we try to set, so to write any object belonging to the other window object, then it will the effect will be like deleting it. Okay, so that's quite weird, but it works like that. And if we have some code like this with some function that checks for something, and then this kind of code, like a condition on check me, if we try to from the attacker frame to overwrite check me, it will have the effect to be deleted. So this will be undefined and will trigger the exception. So if we have a bug here. We have changed the flow. Another interesting thing is that we can, from the outer frame, we can overwrite ourselves with the top opener, parent, and frames, and the frames also in Opera. So if a victim page assumes that something has to be taken from the window top or the window top opener, parent or frames, you can actually trick the victim page into believing that everything is going okay because the outer frame is belonging to the same host. Okay. So, for example, let's see if the victim page contains something like this. So, parent or opener or whatever. Reference to the object, the opener window, and then trying to get the frames with the parameter, and then writing it into the document. Actually, the attacker from the attacking window can just overwrite the frame object with what he wants, and the attack will be written in the victim context. Okay. Okay, this is for Firefox. For Internet Explorer, there was this interesting. There's some object which can be overwritten, but the most interesting is the opener object, because there are several JavaScript-based application that assumes that they are opened by another window. And for example, TinyMCE and FCK editor have JavaScript in it that assumes that. So we can actually try to, for example, overwrite a method, and if let's suppose a window, a pop-up window form that is just JavaScript, and that it sends by using a method some sensitive data to the opener object, to the opener window. So we can an attacker just can overwrite the opener object and recreate the method function, the method, and it will get the sensitive data back to it. Of course, it can be used as cross-site scripting, DOM-based cross-site scripting, because if the victim has some opener data attribute, which is going to be written in the document, we can just do something like this. So, no, we don't have the window. Okay, it was supposed to be, there was supposed to be a demo, but we forgot to start the VMware. So this is the screenshot of the TinyMCE plugin exploit by overwriting the opener object. I just can maybe show you maybe okay, opener, tiny, okay, so just to here we set the content location of the frame to the victim scripts, of course the flowed script, okay, which is paste text. Then we overwrite the opener object of the attacker window with this structure. In this case, we had to overwrite several objects because the flow should go okay, so no exception should be triggered and so on. So it's kind of like trial and error, but the effective method, which is overwritten and that returns the payload, is this one, adver. Okay. So it's a trial and error. You have to construct, you have to build the opener object in order to perform the attack. Okay. Okay. Now Safari Air WebKit, it was fixed, but it's still interesting. There was this stuff that an attacker could use the find getter in order to overwrite history back, go forward, and item. Okay, so if the victims, and that was this is quite common, no? Uses the history back function, the attacker could overwrite the getter and execute by using the eval function of the victim's frame, which is executed in the context of the victim. So, and no exception, same origin policy violation is triggered. This one got executed in the victim context. This is fixed, okay, but is interesting because it's the use of every kind of feature which is blocked or allowed by a browser or another browser, but the thing is that if a vendor forgets to block some communication between frames, and it could be the apocalypse. On Opera, the top object could be overwritten. This could lead to frame buster, which means that every kind of anti-framing is quite bypassable, quite easily bypassable, and DOM-based cross-scripting. So you know what a frame buster code is, something like this one, okay? If top not equal self, then let's reset the top location. But since the top object can be overwritten under Opera, you can just use a race condition in order to set the top reference to the self-reference of the victim window. So this is going to be equal, and it will be bypassed, okay? So welcome back, clickjacking. Another interesting thing is that since you can overwrite the top object, you can redefine methods. And since you can redefine methods, there's this nice code that gets executed in the victim context. So if the victim just called top focus, the method is executed in the victim context. Why? Similar to the defined getter payload of Safari, because of window 0 is itself. So it's allowed to be executed eval. This is just a screenshot of a proof of concept. Okay, on Google Chrome, there's a guy that found that there's a way to exploit the frame buster by using the defined setter of location of the top frame, so the attacker frame. Okay, the interesting thing here is that probably, well, it's based on trusted relationships about the application and the window reference, okay? So the victim thinks that it's been called by a legit site, okay? And it's due to the lack of standard for defining the policy of what has to be accessed and what not, okay? The good news is that probably if I did this research in 2006, a lot of other objects were writable or readable. The new version will allow only send message or post message, which is cross-frame communication method, which is a standard of HTML. No? But there are only a few other things to fix. Okay. Now let's reverse the reasoning. Let's see if we can use what's the HTML feature, rich internet application features, in order to exploit them by using some kind of technique. For example, Opera implemented this input element with the new type attribute, which is email and URL. If a user just press a key inside the input, you get the same as the location bar. Okay, so the history actually. So how to steal those very interesting data? By using the focus stealing technique. Set the onKey down event on the window, set the focus to the input URL element in order for the key code to be the enter key, because the only problem with this interaction is that you can just press S and then use up and down cursor keys or the mouse and then enter or the left click. So there is no way to control directly by JavaScript. So we have to entice the user to do something in order to steal the data. If the user presses enter key, then let's steal the data by using a simple value attribute, which is readable, and then set a new random or specific value inside the input object. So, how to force a user to press up, down, and enter keys in order to steal data? Let's see. Here it is. Okay, let's use a game. For this game, you have to use the cursor keys and the enter in order to fire. Okay, this is a JavaScript game. So, down here, you see the input element, and I just put it outside of the window. Okay. Then we use the user hi, I am the victim. I just press enter and I begin. You will see, yeah, you will see here. I'm sorry, but yes, there's some problem. Here it is. Okay, you will see here the history still at the stolen history. Okay, here it is. So if I do, you can see what's happening. Okay, so this is the proof of concept. Okay, and this is here. It is okay. Fortunately, it's just implemented by Opera. Okay. An attacker could steal internal host names, for example, steal sessions if there are in the query string, gain internal IPs, steal the whole history, or focus directly on interesting hosts like, I don't know, Google, banking, and stuff. That should work also on type email, so probably you can steal also your the contact addresses, and I don't know if there's a browser vendor that is planning to implement it, he knows what to do. Okay. Now the attribute selector, I think it's late as usual. I'm going quite fast. CSS attribute selector was is another interesting CSS3. So regarding the rich internet application stuff, and it's been implemented by most of browsers, or all the browsers, and there's this interesting thing that there is the selector with the substring matching, so you can just select an object, a tag with an attribute that begin with some value, that ends with some value, or that contains some value. Given this, it's quite it's easily understandable that we can abuse this functionality in order to infer and read by inferring the attribute values of a page without JavaScript, without using JavaScript. Okay, let's see now, babe. Well, it's 5 seconds, so. It's 5 seconds. 5 seconds from now. Okay, this is without JavaScript, and there is a meta refresh, which is getting by inferring the content of an hidden attribute, okay, and I don't know, yeah, and that's the result, okay, very easy. Okay, now it's up to you.
All right, so we wanted to talk a bit about Google Gears as well. Google Gears is a browser plugin that Google develops to make developing rich internet applications easier. It includes a bunch of different functionality. We'll only talk about some. since we presented this a while ago, Google's already fixed some things. I'll just leave that in the slides for anyone who's interested. But one of the more interesting things Google Gears allows, is it allows cache poisoning by design once you have an XSS bug somewhere. This is particularly interesting because a lot of different domains have trust relationships between each other by, for example, pointing script tags across domain. One of the ones I want to demo is a trust relationship between google.com and gmodules.com. Given gmodules.com is a domain that's completely designed to have user input on there and user script on there, it's meant to host completely untrusted data. It's pretty much irresponsible of Google to rely on it, but they have. And using the functionality provided to us by Google Gears, we can jump from the gmodules domain to the google.com domain. So how do I get out of this?
Three? No.
No,
okay.
it doesn't matter. Okay, right. The one thing with Google Gears is the first time you use it from a given domain, Google asks you, are you sure you want to let this domain store some kind of data on your computer? This really isn't clear because it's in Italian. Hell, I can't read it, but I think that's the yes button. So anyway, so what this page does, it's on the gmodules.com domain. I'll just try again. Yeah, okay, good idea. Alright, so what this control does is it uses the local server object that Google Gears gives you, which effectively just allows you to capture our malicious payload from this particular URL that's on the same domain. And once it's done capturing it, we rename that file to this other file that a bunch of different pages on the internet include inside a script tag. So if we... If we go there, we see that essentially it's just some JavaScript which alerts whatever domain we're on. So, what? That's cancelled? No, that's cancelled. Okay, right, I totally got this. Right, so we go to a specific Google URL, which includes this script source and includes our script from that other domain, where we normally wouldn't actually be able to control that URL, but given Google Gears allows us to play with the cache, we can now say that we can now rename things there, and whenever people go to this page and have their cache poisoned, our XSS will execute. I found that originally here, but amusingly, since I left my own computer cache poisoned for a while, I found out that the OWASP website, the Open Web Application Security Project, which tells people what to do, has exactly the same issue. So where were we? Yeah, you use your MacBook. Use every key a second. All right. One thing that is being fixed now is that Google Gears had this functionality to create JavaScript files, to create JavaScript threads from specific files that you could load from a URL. And this could be done across domains. So if you could host some JavaScript on a particular domain, you could have it executed in the context of that particular domain. This has been more or less fixed as a way to conduct XSS because you also need to control the content type header. However, Firefox in 3.1, I'm pretty sure, are trying to implement web workers. Not sure if they're going to have that check or not. But interestingly now, like due to this, hosting plain text is obviously dangerous because we can just put up our JavaScript. Hosting images was dangerous because we could create images that were valid GIF files and valid JavaScript, or valid JPEGs and valid JavaScript. But interestingly, hosting like XML that was properly escaped was also dangerous due to how Firefox has modified its JavaScript parser. Firefox has added support for this thing called E4X, I think it's ECMAScript 4 XML, which essentially gives you a new way of defining objects. As And the way you define them is by XML. So yeah, as you can see up there, the line there creates an object with a bunch of different properties and variables of things. But the interesting part is it allows you to have embedded JavaScript constructors using these braces. So the value in here, once the JavaScript parser actually passes it, would be 3 instead of 1 plus 2. So what we could do, if we could inject somewhere that was valid XML, we could simply inject our braces into that XML, and yeah, and then point the Google Gears web workers at it, and then it'll be executed in the context of the domain where we can inject braces. Particularly interesting because almost no one actually filters braces anywhere. It was especially interesting for sites that did AJAX and actually used the XML portion because they were obviously perfectly valid XML. This isn't so useful for this particular attack now since it's fixed, but in web workers. But this is interesting to us because this means that if, when we're doing some kind of cache poisoning and we want to abuse these kind of trust relationships, if we can't control the whole response, but we can inject braces into some valid XML, we can form valid JavaScript files and then do cache poisoning much easier. Of course, there are some caveats to this because the E4X parser requires fully valid XML and has a bunch of these restrictions, which you can look at in the slides, since we're running out of time. We also had a look at Firefox extensions because these are essentially pieces of trusted code that are written in JavaScript, XUL, and HTML. So cross-site scripting bugs in this kind of functionality result in code execution. The attack surface for these is kind of what you'd expect. If you get an input from the network, such as via the unrestricted XML HTTP requests, or if you get input from a web page, or things like this, then you're dealing with potentially untrusted entities. Common vulnerabilities are when you get some kind of JSON data from the network and then just put it into the eval function to get an object out of it. While this is also common practice in JavaScript apps, this is a much more serious issue here because being able to control the network doesn't mean you have code execution. But if they do something like eval JSON they get from the network, then you have a code execution bug that you can hit if you're on the local network. And similar kind of as injection because you have a lot of different sensitive objects that you might want to play with, like directory traversal, or like there are actual like SQL stores for extensions as well. So one of the things we want to look at is a specific bug that was similar to one another Watchfire guy found about like, I don't know, 4 or 5 months ago, which started me with all this. It was rated as a low-risk vulnerability because there was, they couldn't figure out any way to exploit it. The easiest way when you're attacking some kind of extension to determine if you're actually running in a privileged context is to just have a look at the window object. If your current window object is a Chrome window, then you're running in Chrome, which is a privileged context. If it's just a window object, then it's running in a null context and you can't really do anything usually. So if we have a look at, close all these, can you close them?
Oh, yeah.
I'm sorry, I'm not a Mac user.
Instruments.
Yeah, that's right.
Instruments, temper data.
All right. So, oh no, cancel. God damn. Yeah. Okay. So the bug itself is pretty lame, hence the name of the file. What happens is if you have some kind of malicious file, and then you use the graphing functionality in Tamper Data to like graph them all, you'll result in an XSS bug. The one I'm using is just from the like HTTP headers where you have like 404 not found or 200 OK, you put like just some number, then your XSS and it'll get executed. the reason I say this bug is lame is pretty much because it requires way too much user interaction to be useful. But when we go have a look at the window, we'll see that it's a fairly valid assumption to think that this bug is unexploitable, because when you have a look at the context, where is it selected, you get just a normal window object. So if you're doing just a typical analysis, yes, this is running as completely untrusted code and you can't do anything useful. Using the same type of things we talked about before, there are bugs in like Firefox which are usually typically low impact, but there are bugs in the access controls that allow us. Oh wait, we had to use this first. See, like I have to try to get owned here. So yeah, where is it? Oh wait. What just happened? There it is. Right. So we were actually able to write an exploit which set this entry in the configuration of Firefox. Config. Blah, blah, blah. Which said essentially the URL that Firefox gets updates from to whatever string we wanted. The default is this like SSL URL, and so Firefox updates are pretty much protected by the fact that you can't usually edit this config entry and it goes over SSL. So essentially when you go, right, how do I open that file? I need to open that PHP file. Oh. TD. Okay, right. So yeah, you can't really see that. Okay, right. So the XSS bug is here right after, like, in the HTTP headers. To exploit this, what we did, I pretty much used the same techniques that Stefano did to have a look at the access controls of the opener object in Firefox. So what I found was that in the opener object, all the browser default objects in there were properly protected, but any objects created by the extension had absolutely no access controls on them. So I could set any variables I wanted. So after fiddling around, I found out that you could also execute functions. And when you executed these functions, they executed in the privilege context. So we were able to edit all the variables in that context, so essentially control all the data those functions are working with and then call them. So we essentially say we want to edit the root preferences from nothing, then we want to set the particular config entry to whatever we want. And this essentially makes a bug that's typically considered completely unexploitable give us a path to code execution, since once we change where a user gets updates from, well, next time they open their browser, they're going to get their updates from us, right? Wait. Do we have to stop yet, or no? We have... Yeah, right. Okay, yeah, essentially, once you actually have typical code execution inside the privileged context, you can just like run executables, do whatever the hell you want. It's pretty easy from that stage. As a side note, given that JavaScript can be privileged, if you can overflow into the context markers and change them, then that would be potentially one way to defeat dep and other things which stop x86 execution. And since we've run out of time, we'll probably just stop that there and let you have a look at them if you... Yeah. Oh, wait. I say we take a because
okay.
That's also...
Just 2 words about the Opera exploitation, which was researched a couple of months ago. It's about the Opera 6.0, 9.6.0. And what was the problem is, the problem was that it was taught as unexploitable because it was in the Opera history search, but the interesting thing is that when there is the same origin policy, it's about protocol, host, and port. But if we have Opera and nothing else, so the Opera scheme, the Opera protocol, we will have Opera, null, and null, which is the same origin policy of every kind of feature of the Opera browser. Okay, so Opera cache, config, and so on. So the interesting thing is that we can interact in an iframe with the Opera config, and then we can set preferences to, for example, for mail to something else, and get the execution code done. So, read the conclusion, and since it's finished, if you have some question. Thank you.